Hi, welcome to the video for 11.2 and 11.5. So for 11.2, we are looking at taking the derivative of exponential functions, so specifically e to the x. Alright, so the derivative of e to the x is just e to the x. It's not super interesting. However, if you replace the exponent with a function, then we're going to have to use the chain rule. So we're going to leave the inside alone and then multiply by the derivative of that inside function. So let's look at a couple examples. So first, we want to find y prime given e to the 6x squared. So that 6x squared is going to be our inside function. So when we take the derivative, that is going to be, well, the derivative of e is just e to the whatever it's being raised to times the derivative of this inside function, which is going to be 12x. We could leave it like that. It's usually good to put your coefficients in the front, and that would be your solution. All right, let's take a look at the next example. So on this next one, we want to find the derivative. Again, we have 3 times our function, and then we have e raised to a different function. So remember, when you're taking the derivative, if you're multiplying by a constant, that constant just hangs out, times e to the, well, the derivative of e to the anything is just e to that. So we leave that alone. Times, now we need to multiply by the derivative of this inside function. We're going to have to use the chain rule, so we're going to pull that 4 down in front. Remember, the chain rule tells you to leave the inside alone. And then multiply by the next inside. So it's going to be, whoops. There we go. That's going to be 3x squared. Now again, we're going to clean up our answers, so we want to move all these coefficients out in the front. So 3 times 3 is 9, times 4 is going to give us 36, x squared, times x to the third plus 6 to the third, times e to the x to the third plus 6 to the fourth. So that's a nicer way to write our answer. Alright, going to give myself a little bit of room here, or a little bit more room. So, the next question asks us to find the relative maxes and mins of this function. So first, we need to find the derivative. So that's going to be the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Now, before we start finding the relative maxes and mins, what I'm going to do is I'm going to factor this a little bit. The top has a 7 e to the x in common for both those pieces. So that's going to give me 7 e to the x times, when I take that 7 and that e to the x out of this, I'm left with an x. Here, I'm just going to be left with a 1 divided by 49x squared. Now, when you're looking for relative maxes and mins, you're going to set this equal to 0. Now, there's 2 things we're going to be looking out for. We're going to be looking out for when the top gives us 0, and we're also going to be looking out for when the bottom equals 0. So that's going to give us 2 x values. We're going to have x equals 1, and the bottom will equal 0 when x equals 0. Now remember, we're going to take those values, make a nice little sign chart, so 0, 1. Pick some numbers on either side of these, and see if we have a maximum or a minimum. So first, let's choose a value over here, so let's do -1. Let's do 0.5. And over here, let's do 3. So if I take -1 and I plug it in my function, that's going to give me a negative value. Okay? All right. So if I take -1 and I plug it into my derivative, that's going to give me a negative number on the top and a positive number on the value on the bottom, so that's going to give me a negative. If I plug in 0.5, that's going to give me a negative value on the top and a positive value on the bottom, so that's going to give me a negative again. And if I plug in 3, that's going to give me a positive on the top and a positive on the bottom. Now, something to point out is that 0 definitely gives me some interesting information about my function. And what that actually is going to be is it's going to be an asymptote. The reason is that I can't plug 0 into my original function. So that's actually not going to be a maximum or a minimum. Here, though, my function is going to be decreasing and then increasing. So when x equals 1, I will have a relative minimum. All right, the next question, which is going to be the last one for 11.2, is going to say, find the marginal cost at $400 and interpret. So remember, when we want to find the marginal cost, we have to find the derivative of our cost function, which is given above. So here we have 40x times e to the x over 5. So what we're going to do here is we're going to have to use a product rule. So we're going to have the derivative of the first part times the second part left alone, plus the first part left alone times the derivative of the second part. So the derivative is e to the x over 5 times the derivative of x over 5, which is going to be 1/5. The reason is that you can rewrite x divided by 5 as 1/5 x. All right, now for the next section, which is 11.5, what I suggest you do before you start this start this section is go ahead and download or just grab it from your textbook. I have uploaded a cheat sheet, and it tells you how to find the elasticity of a market. Okay, so it says if you have the demand function, okay, and you're given a point, then you can find the elasticity of demand given this equation here. As well, down below, it tells you what each value of elasticity means. So if your elasticity is greater than 1, that means you have an elastic demand. If your demand is less than 1, it's inelastic, and if it equals 1, it's unitary elastic. So what do those mean when we're discussing revenue? Well, what each of them mean is if elasticity is greater than 1, then if the price increases, then the revenue decreases. If the price decreases, then the revenue increases. That means that they have an inverse relationship. If it's inelastic, that means that the price increases, so does the revenue. If the price decreases, so does the revenue. If it's unitary, that means that an increase or decrease in the price will not change the revenue. Okay? So that also means that the revenue is optimized at that point. So let's go ahead and print that out and just keep that next to us. So let's say that we want to find the elasticity of demand function p plus 3q equals 180 at the point q comma p equals 30 comma 90. So I'm going to break this down into steps. So the first thing that you want to do whenever you have a problem like this is you want to solve for q. So in our case, we're going to have q equals 180 minus p divided by 3. So you want to solve this equation here for q. And you're going to get q equals 60 minus 1/3 p. Now, the second thing you want to do is that you want to find the derivative. So find q prime, which, by the way, another way we write that is dq over dp. So if we find the derivative of this function here, we're going to get that it's negative 1/3. Now the third step is that you're going to take that and you're going to plug it in to find your eta. That's that fancy looking n right there. So eta is negative p over q times dq over dp, and what you want to do is that you want to plug in your point q comma p that they gave you. So in our case, negative p over q is going to be negative 90 over 30 times, and then what our dq over dp is it's going to be negative 1/3, which, if we do the math on this is going to end up giving us a positive 1. So how will a price increase affect the total revenue? Well, let's hop back to our cheat sheet. Now in this case we have unitary elasticity because we got that eta equals 1. So what that means is if a price increase happens or a price decrease happens, it won't change the revenue. So how will a price increase affect the total net revenue? It will have no effect. Okay, great. Now for number 2, we want to find the elasticity of the demand function p squared plus 2p, or I'm sorry, p squared plus 2q plus, nope, I was right. Find the elasticity of the demand function p squared plus 2p plus q equals 70 at p equals 5. So first, just like last time, we want to solve for q. So we're going to have q equals 70 minus 2p minus p squared. Now the second thing we want to do is that we actually want to find q. So they gave us p, but we want to find q. So q is going to equal, well, they told us that p equals 5. So that's going to be 70 minus 2 times 5 minus 5 squared. So we get q equals 35. Okay, now we're going to go on to the third step, which is that we want to find q prime, which, remember, that's the same thing as dq over dp, which in our case is going to be negative 2 minus 2p. And now the fourth step is that we want to plug it all in. So remember, our eta is going to equal negative p over q times dq over dp, so it's going to be times negative 2 minus 2p. So we want to plug in our q value, which is 35, and our p value, which is 5. So that's going to give us negative 5 divided by 35 times negative 2 times 5 minus 2. So what we end up getting is that our eta value is roughly 1.714. Now again, the question is, how will a price increase affect the total revenue? So let's go back to our cheat sheet. Well, since our eta is greater than 1, that means that we have an elastic price. So what that says is if the price increases, the revenue will decrease. So if a price increases, the total revenue will decrease. All right, we have one more example. Gotta give myself a lot of room for this one. It's pretty involved. So if the weekly demand function, so first off, demand function is p equals 86 minus q, and the supply function before taxation is p equals 2 plus 6q, what tax per item will maximize the total tax revenue? So when you look at this cheat sheet, what you're going to be doing is going through this maximizing total tax revenue step by step. So I would go ahead and have this next to you, and we're going to go through it together. So first, what we want to do is write the supply price after taxes. So our price for the supply function, that's that blue one here, is going to be p equals 2 plus 6q, but remember, we have to add taxes to it, so we're going to say plus t. Now the second step is that we want to set the function's equal and solve for t. So here's why we want to do that. Remember that you're going to be maximizing your revenue when your demand is equal to your supply. So we're going to take supply and we're going to set it equal to our demand function. So what that means is that we're going to take 86 minus q and set that equal to our supply function with the taxes. Now, since the taxes, t, are the things we want to maximize, we want to solve for t here. So that's the whole purpose of this step. So if we move everything over and solve for t, we're going to have t equals 86 minus q minus 2 minus 6q. So we get that the taxes per item are going to be 84 minus 7q. The third step is that we want to write a function for the total tax revenue. So that's going to be a big T. Now, the total tax revenue is that we're going to take the taxes we make per item times the amount of items we sell. So that's going to be T, the tax, times how many items we sell. Now we want this all to be in terms of just Q. So that's going to be 84 minus 7Q times Q, which will give us 84Q minus 7Q squared. So remember, little t is the taxes per item, okay? Big T is the overall total taxes that we get. Okay, now the fourth step is that we want to maximize the tax revenue. So remember, whenever you see the word maximize, you want to take the derivative. So t prime is going to be 84 minus 14q. Now, since we're maximizing this, after we take the derivative, we want to set that equal to 0. And we want to solve for q. And when we do that, we get that q should equal 6. Now, that's not our answer because we still want to know, hey man, when t equals 6, what should our taxes be? Okay? So, when q equals 6, what are our taxes going to be? I'm just going to go ahead and erase this so I have some more room. So we get 0 equals 84 minus 14q, which means q has to equal 6. Now the fifth step is sub q and find t. So how we do that is that right above, we're like, hey, did you know that t equals 84 minus 7q? So we're just going to plug in q equals 6. So t equals 84 minus 7 times 6, which is going to give us 42. So in order to maximize tax revenue, we should tax $42 on each item. Awesome, and there you have it. So it seems like a lot, but remember, there was a reason for every single step, and it's pretty formulaic, which means that you're going to go step by step and complete every step just like you saw it here. So don't forget. Supply, add the t to it, set the functions equal your supply and demand and solve for t. Multiply t times q so that you get the total amount of tax revenue. Take the derivative to find what it's maxed. Use that q to find your t.